Hi everyone. So my name's Eva and I am your replacement for half of this section of the evening, so I'll do my best to edutain you. So I am a research scientist. That's the last joke you're getting from me. I'm a research scientist, but more specifically I am an electron microscopist. Which means I use really, really fancy microscopes that use electrons rather than light to look at things that are super, super duper small. Okay. I have a picture of an electron microscope. Right, oh no, back there, gone too far. Go back. Okay, this is my colleague Chris, using our electron microscope, the Untitled microscope in Trinity, just earlier today. This is a very recent photo. Pretty excited. Unfortunately, Chris could not make it tonight. Sorry, ladies. So what we do is we get electrons, just find them forever. We accelerate them down this column. They pass through a teeny tiny little sample here. And then we're able to look, by looking at the electrons that pass through that sample, we're able to try and visualize things that are really, really, really small. And yeah, thanks. This is an image here of a very, very thin flake of indium selenide. It's so thin that we call it two-dimensional, because we don't need the third dimension. Come on, please. And if we zoom in even further, we can see all those little dots there are actual columns of atoms. So we are actually getting down to like atomic scale, sub-nanometer scale, which is pretty cool. Now, some of you may have realised that, sorry, I don't know why I did that. Some of you will realise if I were to like shoot a beam of high-speed electrons at you right now, very few of those electrons, none of those electrons would actually reach you because we're in air. Those electrons they'll bump into air molecules, they'll be deflected, they'll be absorbed, they'll lose their energy. So in the microscope, we've got to keep things at a really, really low. We want our electrons, when they leave the gun up here, we want them to still be going really, really fast when they get down to our sample down here. We need that obviously to be in a vacuum, a very, very, very high vacuum or a very, very, very low pressure. So we want no like air or gas molecules knocking around in there for the electrons to bump into. And the pressure in there would be about a billionth of the pressure in this room right now. So like really low pressure, wow. And so basically there would be just very, very few gas or air molecules in there. And we can get to that low pressure mostly using pumps, just sucking out the air and sucking out the gas. But that doesn't get us quite close enough. We've one last piece of technology called cold finger, which I visualize probably completely incorrectly as a metal thing exactly in the shape of my finger that sticks into the column of the microscope, and it's connected to copper wires outside of the column of the microscope that we keep really, really cold. We put them in a cold liquid because metal is a very good conductor of heat. That cools the cold finger down, and any sort of contaminants or anything that are in the column will condense onto the cold finger and keep it all nice and clean. Now, can anyone guess what liquid we use to keep the cold finger really, really cold?
Nitrogen.
Liquid nitrogen, yay! Okay. So I was thinking today about what I would talk about. I was thinking about what we do in our lab and what's really cool. And yeah, like the electron microscope's pretty cool, and looking at things on an atomic scale is kind of cool. But you know what's really cool is liquid nitrogen. So I thought I'd bring some liquid nitrogen to show you today. We had a minor spillage, so I don't know as much as I wanted to. But anyway, we'll talk about it anyway. It's amazing. It's really cool. It's not just really cool. It's really, really fucking cold. It's like I'm going to do a little health and safety thing here now, because it's like minus 200 degrees Celsius. And extreme cold is as dangerous as extreme heat, so you can burn yourself. So don't drink it, don't put it in your mouth, don't put it in your eyes, don't throw it in your friend's face to be hilarious, don't stick your finger in it, you've got frostbite, and then everything will be great. Sorry. So here is some liquid nitrogen. I know you can't all see, maybe at the break some of you can come up and play with liquid nitrogen with me, if you can be sensible. So I'm holding, this is a styrofoam cup of liquid nitrogen. Styrofoam is a very good insulator. We used to always use it for like takeaway tea and coffee, but it's really bad for the environment, so we don't use it very much anymore. But it is good insulator, so that's why I'm able to hold the cup in my hand without hurting myself. And if you see there's like, you can see the vapours coming off it, but so it is actually, even though it's minus 200 degrees Celsius, it is actually boiling. Like it's liquid turning into a gas, and you'll see the vapours when they come off, they're actually falling rather than rising. So if I had a steaming cup of hot coffee here, the vapours would be rising, they're falling. So like, we're getting some science in here, guys, you're learning. And if I were to add some heat to this, I can make more vapours come off. So now, I'm going to pass this around. This is where the health and safety really comes in, guys. Just blow into it, don't drink it, don't stick your finger in it, please. Just be sensible, guys. There you go. Just blow into it and pass it on. You can make the vapours with it. Okay. Now we're going to talk about what happens when we put, like, I guess, what would you call it, an organic substance into liquid nitrogen. And here I have a banana that's been sitting in this liquid nitrogen for quite some time. And I'm going to use this banana to do something you don't normally do with a banana. I just realised what that sounded like. Oh my gosh. I am going to use this banana to hammer a nail into a piece of wood. Okay, just okay. So this banana has been at a really, really, really cold temperature. Normally if I were to hammer, using a banana as a hammer, the nail would just go into the banana and it would be a disaster. Whereas now, we'll see what happens.
Wow.
It's amazing! Yeah. And just an example of what could happen if you stuck your finger into the liquid nitrogen for a while. This is a banana that I put into liquid nitrogen earlier. So it just goes all gross and black. So yeah, it's just good.
Don't do that.
Don't do that. This is my lovely assistant, Aisling, by the way. These flowers I'm destroying, but it's all for fun. Don't worry.
Science.
It's for science. Science. Science, fun. Same thing. That's why she's my assistant. She can't see. Okay, so here we have a flower.
That's so cool.
It breaks up like glass. Wow. Yeah. So. And this is pretty cool. You can see now, in the bowl, the liquid nitrogen bubbling away. Ooh, it's pretty cool. And our last thing I'm going to do, I'm going to pour more liquid nitrogen in there. And I have, here I have a balloon. Would anyone like to guess what's going to happen to the balloon if I put it in the liquid nitrogen?
Change colour. Wow.
Actually, I'll try and hold this up so you can see this better. So, you can see it's... Does anyone know why it's shrinking? Anyone want to explain to us?
That's in the air.
Yeah, this is the air inside it is all like shrinking, getting smaller and smaller and smaller. And I'm going to take it out and we'll see what happens to it. And actually there's a little bit of water inside there as well, because like the water vapor that was in there is like condensed into water now. And then it's a balloon again. And there we go. And now you can play with it like a normal balloon. Okay, so I know like not all of you could see that well, so I have got a little bit more liquid nitrogen here, so maybe during the break after Phil, somebody could come up and play. If you can be sensible, you can play with the liquid nitrogen, we can all have a great time. So
She's angry.
Very
Does anyone like 3D puzzles? And it's physical change, not chemical change, because it goes back to normal afterwards. It's still a block.